Okay. So, till now in this course we have talked about different tools, I will say, which are used in machine learning. Tools such as sampling method. Samplings are tools basically. You can use it in machine learning, you can use it in other places also. Tools such as approximate inference algorithms, expectation propagation, variational inference. Tools such as Bayesian inference itself is a tool actually. And that is what we have been focusing on till now in the course, and we have been focusing on those with Bayesian linear regression in mind. But you have to be careful and you need to be aware that these tools are not only tools that can be used with Bayesian linear regression, you can use it even for unsupervised learning, you can use it in uncertainty quantification, nothing to do with machine learning, and so on and so forth. So, it is not like these tools are only for probabilistic machine learning, these tools are generic. Yes, probabilistic machine learning is probably the one place where these tools are used in abundance, but does not mean that probabilistic machine learning is the only place for this. And that is why in any statistics or statistical computing book you take, which is there much longer than machine learning, you will find these tools. I mean, the term machine learning came in, or the term AI came in 1956. Markov discovered that in 1907. So, definitely these are not related to AI, these are used in AI, right. But starting today and for the remaining of the course, we will be talking about techniques and tools that are basically machine learning techniques. So, techniques and tools that are for machine learning. In other places you will not find their application until and unless it is application of machine learning for some problem XYZ, application of machine learning for, let us say, fluid mechanics, application of machine learning for solid design, for topology optimization, and so on and so forth. Okay. So, long story short, starting today we are going to talk about some machine learning techniques, probabilistic machine learning techniques, and you will see that whatever we have learned, those are used in one way or the other. In particular, I will be covering two of the most popular techniques in machine learning. The first one is Gaussian process, we will start with that, and then the other one will be neural network, but probabilistic neural networks, that I will cover towards the end. So, first we will wrap up Gaussian process, 3 to 4 5 lectures, and remaining 3 lectures maybe, or 4 lectures on neural network, okay, or probabilistic neural network. So, that is the idea. So, with that background, let us start with Gaussian process. Okay. Before proceeding, remember that on Saturday we are following Wednesday routine, which means there will be practical, but in the practical session I will be taking lectures, because I missed 2 lectures. So, those will be covered to make up for the missed lectures. We will have lecture on during the practical time. The venue will be announced, it might be here or it might be where we have practicals. So, that we will decide later. Okay. Okay. So, we are going to talk about Gaussian process. To talk about Gaussian process, first we need to understand what is a process. We have talked about Gaussian random variable. What is a Gaussian random variable? A random variable with certain form of PDF, which is symmetric, mode mean and median are same, and all those properties hold, right. And we have done it for univariate case and we have done it for multivariate case, right. Today we are talking about Gaussian process. So, for first question that should come to your mind is that, is there any relation between Gaussian process and Gaussian random variable? We will try to address that. But first, what is a process? So, generally, so any idea what is a process before I give you the answer? When you hear process, what comes to your mind? You associate time with it. For any process there is a time aspect, right. So, when you say about process, it is in some sense having some dependence on time. So, when you talk about random process, you can think of it as a variable which is random, but which also changes with time. So, when I talk about so for example, if I write a random variable, If I write a random variable, I generally write it as x, right? X is a random variable, let us say. Think about the coin tossing example. The outcome of a random variable will be some number 0 or 1 in this case, in the case of coin tossing, where 0 is associated with tail, 1 is associated with head, right? That is random variable, there is no time sense. When you are talking about random variable, you do not associate time with it. But when you write random process, you associate time with it. So, if x is a random process, you will associate x with time, but xt, if I only write xt, that means it is a time series, a deterministic function x, or x is a deterministic function of time. So, to indicate that it is also random, you also associate it with omega, where omega belongs to omega, and omega is, you can think of it as a probability space. Obviously, probability space has three things, I am only writing one. There is f and then there is p also, probability measure. I am only writing omega, so it is some probability space. Okay. So, when I talk about random process, you relate it with something random, but also changing with time, right. So, if I have to summarize this random process, you can think of it as infinite in bracket collection of random variables. You can relate or think of random process as infinite collection of random variables. Why infinite? Because see, there is a dependence on time. You can discretize time, and because time is continuous, if you discretize time, you can have infinite number of discretization in time, and each of these discretization will be function of only omega, which is a random variable. You take a collection of those, that becomes the random process. So, random process, you can think of it as infinite collection of random variable. Okay. And infinite, the term infinite is coming because it is a continuous function of time. So, you can discretize in time to get infinite numbers. That is the idea. Any doubt? Making sense? You are able to follow because new terminologies are being introduced. Now, random process was the original terminology. Later, another terminology came up, which is known as random field. Okay. So, let us discuss that also, although we will not need it, but maybe in homework we will need it. Random field. Now, random process and random field are actually same, there is no difference. But just to differentiate, if you have to differentiate, you will associate field with space, process with time, right. So, if you have to, so you can write it as x, where x is small x, okay, I should not write small x, maybe I should write z or something, I do not know. So, you will write it like this, where this is my spatial coordinate now, spatial coordinate. Okay. Any doubt? So, now based on the discussion till now, can you come up with another interpretation of random process on your own apart from what has been discussed? Can you come up with another interpretation of random process or random field? Same. Another interpretation of random process or random field or both? Can you think of another interpretation? No, that you have to come in, right? You might have give me a new interpretation which I am not thinking about. If I give you clue, I am directing you towards the interpretation I want, but you might have a better interpretation, right? So, any interpretation coming to your mind? What is omega? Random variable, right? So, random omega is denoting that x is random, right? So, if something is random, can we draw sample? Like if it is something is a Gaussian random variable, I can draw Gaussian random sample. If uniform, I can draw uniform random sample. We have talked about sampling method, so we definitely can. So, how will each sample look like? Because it is a random process, so there is random at least. So, if I draw a sample, what do you think that sample will look like?
Draw sample.
One sample, realization. If I draw one realization, one sample from the random process, how do you think it will look like? I will give you a clue.
It's a function of time.
It is a function of time. If it is a univariate Gaussian, the sample will be a scalar. If it is bivariate, then the sample will be a 2D vector. If it is trivariate, 3D, n variate, nd. In this case, it will be a function of time. So, each sample is becoming a function. Then random process is a distribution over function. Let me repeat. If you think about any random variable, you can draw sample. Now, if it is a univariate random variable, Gaussian, let us say, one sample will be a scalar, one number you will get, right. If you throw a dice, you will get 1 or 2 or 3 or 4 or 5 or 6, that is a number, that is a univariate, correct. If I have a bivariate random variable, I will get a 2D, throwing 2 dice, I will get 1 1, 1 2, 2 1, 2 2, something like that, right. If I have n variate distribution, nd Gaussian, let us say, I will get a nd vector, correct. In similarly, following that, if I draw a sample here, I will get a function of time. So, I will get a function or a function of space in the random field case, right. So, each realization is becoming a function. So, that means it is a distribution over function. So, you can think of random process also as a distribution over function. Clear? So, random process can be thought of as distribution over function, right. So, now with this interpretation, what is a Gaussian process? It is a Gaussian distribution over function, as simple as that, right. It is a Gaussian distribution over function, correct. So, Gaussian process GP can be thought of as Gaussian distribution over functions, right, which means each sample will become a function, a deterministic function, correct. So, if I have to draw not a Gaussian process, but a random process, you can think of something like this. Okay. I have 3 dimensions. What are the 3 dimensions? Let us say this is my x, y, z. So, what is x here? Obviously, it is not the x. I will have to. So, what is in the x direction? Let us say. What is this? I can think of it as omega. So, the randomness can be in that direction. What is y? Time. And what is z? The function value, x in our case. Okay. And now how will let us say random process look like? I mean samples, let us say. I am not. So, you can think of a sample like this maybe. So, what is this? A sample of the random process. If I have another sample, a second sample if I draw, that might look something like this. A third sample might look this, right. So, now if I take a single point t, so let us say I take fixed t at some point. So, I will get these points, right. What are these points representing? At a particular time, what will that represent? Sample of what? Of a random variable. I said collection of random, infinite collection. So, if I fix time, that is a random variable now. So, those are samples of the random variable. So, let us say x of t, t1 let us say. If I name this point t1, then this all of these are corresponding to t1 and these are different samples of t1, x of t1. So, this is like different samples of a random variable which is generating from this random process because I am fixing time, correct. And so, there is randomness, clear. If I go in this direction and select omega, some omega, let us say omega 1 or something like that, what will that represent? So, now omega is fixed, but time is changing. So, I will get a deterministic time series. So, each sample will become a deterministic time series, because in this direction there is no randomness because omega is fixed, but time is changing, so the response is changing. So, if I go in this direction for this plot, I am getting a, that is a realization of the random process. So, that is a time series, a single time series, and if I go in this direction, I am getting collection of random samples of a random variable corresponding to x at t1.
Why will it be a deterministic time series? Because omega is over a probability space, right?
That is a fixed value of omega. So, you have drawn a sample. So, once you draw a sample, that is deterministic. Once you throw a dice, you get 1 or 0, that is deterministic, or sorry 1 or 2 or 3 or 4 or 5 or 6. So, that is a realization. Remember that realization of random variables are deterministic. Realization changes if you draw different samples every time, but once you have drawn a sample, that is deterministic, that does not change.
So for a particular omega, that will be a function of time
Only time.
There will be no randomness.
No, because that is a single sample. A sample is deterministic. The variable is probabilistic, but once you draw a sample, samples are deterministic. Yes, it does not mean the sample will remain same. Every time you draw, you will get a different sample, but that is because that is a different sample, that is not the same sample, right. This is sample which is in form of function, it need not be a function if I draw from a random variable. Sample is not restricted to random process, it can be of a random variable also. In this case, the sample will be a function, right, and this is obviously the magnitude, okay. Clear? So, whenever I talk about random process, this diagram should come to your mind, okay. This is the visual representation that should come to your mind, okay. That it is a collection of functions like realizations, right. So, it is a distribution over function. Any doubt? Okay. So, now what problem are we solving again? Till the beginning, regression, right. What is a regression problem? You have some measurements x and y for a new x you want to predict, right. So, think of you can think of it as one second. So, look at this diagram. This is actually showing any generic regression problem. The red points that you are seeing here, right, these are what? Some value of y for some x. So, you have 1, 2, 3, 4, 5 points, and in regression what are you interested in? You are interested in finding out the value of y at some new x. That is the machine learning problem statement for supervised learning regression specifically. In classification it could have been classes, right. So, this is the problem we are solving, and how were we solving it till now? How were we solving it? We have solved this problem. How have we solved it? We have assumed some functional form. In Bayesian linear regression, we parameterize this function with basis function and unknown coefficients, right. And then based on data, we want to find out the unknown coefficients, which is my posterior, and using the posterior, we try to find out my predictive distribution. So, very briefly, if I have to review Bayesian linear regression. So, what we have done is that we have assumed that T is equal to W transpose phi x plus epsilon, where epsilon is Gaussian 0 comma sigma square, and because of this we have probability of D given theta, where theta is W in this case. It comes out to be a Gaussian over y I given x I, not x I, sorry, y I, because I am directly writing the Gaussian. So, W transpose phi of x I comma sigma square, and you do a product over I, you have n data points, right. You assume some prior, I am not writing what you assume, but you can assume let us say a conjugate prior, or you can assume some sparsity promoting prior or something like that, and then you compute the posterior right, and this is what all the tools we have discussed till now is for this step only, approximate inference, sampling, everything is for this step. And once you have this, you can find out probability of y star given x star comma data, and that is equal to integration probability of y star given x star comma theta, probability of theta given d theta, right. These are the 4 steps we have been following since the beginning of the course, right, and we have been following it very obediently. But do you see any potential problem with this step, or rather with this method, not the steps, but rather the methods? Do you see any potential limitations of this method, or do you think it is perfect? Obviously, it is not perfect, then there would be no Gaussian process. So, what are the limitations? Can you point out at least one limitation of this? See, to use this method, you have to select phi, the basis function, right. And although it can quantify uncertainty and all those things, but your final result is function of your choice of the basis function. Not only the choice of basis function, the basis function can go up to infinite. So, it will also truncate it. So, where to truncate? So, generally what we do, we truncate up to order 3, order 4, order 5, something like that. But what if I am trying to approximate a function which is x to the power 100? Y is equal to x to the power 100. So, the lower order terms are to be truncated, only the x to the power 100 is to be retained. Then what will happen? What will happen is that your whole result is dependent on your decision on what basis to select and up to what order of basis to select or where to truncate, and your all the results are dependent on this, right. And this is why neural network is so powerful. Just to going a little bit sidetrack, because in neural network you do not have to choose basis function. It is more like neural network learns basis function, because the hidden layers and all those things, they are kind of learning basis function. Whereas in this case you have to choose, and that is a problem. In Gaussian process or Gaussian process, neural network, all these advanced machine learning techniques tries to address this issue. The idea of Gaussian process or machine learning is, can we address this limitation? Okay. And in Gaussian process, the question that you ask is very simple. Can we use all the properties of Gaussian distribution that we might have studied to solve the regression problem without needing any basis? Okay. So, the idea is, in Gaussian process, not Gaussian process, in Gaussian process regression, the idea is, can we use the properties of Gaussian, that is all, to solve regression problem or to solve classification problem. In class, I will be only covering up to regression. In homework, there is a classification problem I have given. So, that is your self study part. Okay. The notes are obviously there at the end of the today's lecture. So, there are some notes on classification also. Okay. The problem statement is clear. We want to solve the same regression problem, we want to solve this problem only, but by using Gaussian distribution.
So, but
Assuming what? I am not saying by assuming Gaussian distribution, I am saying by using Gaussian distribution.
But still there is some starting point. So how can we say that this is better than?
No, I cannot say that. I cannot say that. But you do not need to select basis function.
No.
At least that I can say. Second, Gaussian process is a which is a distribution over
A function.
what function? Is there a limitation on that function? Yes, the only limitation is that at each point it should be Gaussian, but in this direction what is the limitation? It might seem there is no, there are, obviously we will come to that, but in general you are not selecting basis function anymore. So, you do not have to truncate anything. When I am saying let us assume it to be Gaussian, are you truncating it anywhere? Are you selecting what all polynomial orders would be there? So, all those issues are gone. But yes, some smoothness and all those kind of limitations are there with Gaussian, and that is why neural network is there, obviously. But even in neural network, how many hidden layers? That decision will anyways come. The idea is which decision is easy to make, which decision is less restrictive. It is not about removing the limitation, it is about relaxing the limitation, right. So, we want to solve this problem only, and we want to solve it with Gaussian distribution. Properties of Gaussian distribution, plain on old Gaussian, and can we solve it with that? Okay. So, basically this is what we are looking at. I mean, this is the kind of plot we want, right, that this I should have a predictive mean which should be with something like blue line that you see, and then I should have a confidence interval, the uncertainty. The uncertainty should be due to what should be the reason of the uncertainty? There are two reasons. What are the two reasons? Noise and lack of data, limited data and noise in data. And that is why what do you see here? If the noise in data is less, wherever there is data, the uncertainty should go to 0, or if the noise is less, it should be very less. Do you see that? Wherever the red dots are, the uncertainty is kind of getting stitched together, and wherever there is no data or away from the data, the uncertainty is increasing. So, lack of data. So, we want something like this, right, but we do not want to select basis function because that is restrictive. So, we want to relax that restriction to a certain degree, clear. So, let us come to Gaussian distribution now, no regression, nothing, right, just Gaussian distribution. Okay. So, what you see on the screen, top equation, right, top left, what is that? What kind of Gaussian distribution is that? What is the mean? 0. Covariance you can see on the right. So, what do you expect from that covariance? Just by looking at that covariance. Positively correlated, otherwise it should have been negative. Anything else? I will say highly correlated, 0.7 is a high correlation, right. So, as a result, if you plot, do a scatter plot of x and y or x1 and x2, let us say, how do you think it will look? Positively correlated, so 45-degree angle, close to that it should be, and this spread should be less because they are correlated. Isn't that what you are saying here at the bottom? That is what you are saying. What do you expect if I make that 0.7 to be 0.9? What will happen to this plot? It will shrink. If I make it 1, it will be straight line, right, clear. What do you expect if I make it 0.6? What is happening? So, the spread will increase. 0.4, right, 0.1, almost circle, almost uncorrelated, and 0 will be exactly circle, correct. So, this is what you see if you do a scatter plot of 2D Gaussian. Why 2D, why not 3D? I cannot show you, visualize, right. So, visualization, remember that is the limitation, okay. 10D obviously nothing I can do, but to 3D I can still try, 10D obviously I cannot do anything, right. So, this spread that you see is controlled by the covariance, right. That is what is controlling this. So, now what do you think this plot is representing? You tell. By the way, these slides are taken from one famous lecture by a faculty in Cambridge. Okay. So he made these slides, I did not. Disclaimer. Okay. So yeah. So what do you think this plot is showing? It is a 0.71 that you can see, but there is some additional lines. What do you think that is showing? What is it showing? The red line you can see there, right? What is the red line showing? This line, right? What is that showing? Homework practical 0, I think you did it. Conditional distribution, probability of x2 given x1. x1 you are fixing, so it is here, and x2. And what is the conditional distribution if the joint is Gaussian? Gaussian. Conditional, marginal, everything is Gaussian, and that is why now come to the point, why are you using Gaussian process? Because these properties are there. If I use something else, this property might not be there, will not be there. Okay. So now, if I draw samples from this probability of y2 given y1 equal to 1, right? 1, right? Yeah. So if I draw samples, how will the samples look like? Where will the samples reside? If I draw samples from probability of y2 given y1 equal to 1, how will the samples look like? Or where will the samples reside? That is the actual question. It should reside on line 1D. So plane becomes line. So it should reside on this, right? That is what you are saying. You see the dots, can you see? So there is one dot here, some dots here. So all the samples are along this line, and naturally so, because then only it is y2 given y1 equal to 1, right? And now if you keep on reducing the covariance like before, what do you see is happening? What do you think is happening? Shape was previously also changing. You have to talk about conditional now. So in the conditional, what do you think is happening? The spread is increasing, which means variance is increasing, and it is increasing because they are independent. Because if they are not independent, so if they are highly dependent, so fixing y1 also means that you are restricting y2, isn't it? Because they are correlated. So if you are fixing y1, that is also equivalent to fixing or restricting y2, correct? But if they are uncorrelated, so whether you fix y1 or y2 should not matter. So that is the 0 1, and if you reduce correlation, the spread should increase. Normal common sense. So that is what you are seeing here. So you will see the spread is increasing, right? This was for 2D. Now, what is the problem with this? As I said earlier, the problem is that 2D is very less. If you have to go to Gaussian process, it has to be infinite dimensional, at least 10, 20, 100 dimensional, and how do you even represent 100 dimensional? You cannot represent at least in this form, right? So that is why there was a new visualization that was proposed, okay? And the idea is as follows. So this is 2D, I am going to represent it like this. So what do you think this is representing? What do you think one is representing? I have given the arrow and all those things. So try to follow the arrow and try to come up with the answer. What do you think this is representing? 1 is representing y1. So that is why this distance I have taken it and rotated it. So 1 here variable index, right? 1 is y1. Then what will be 2 here? y2, and that should be equal to this distance, follow the marker, right? Clear? So now what do you have? This point that you see here, black point, now how is it represented? As a line. It may not be straight. In this case, that is a coincidence straight. It may not be. The sample could have been here, or somewhere. It may not be in the 45-degree line. In that case, it may not be a straight line. It will only be straight if it's 45-degree line, right? Then y1 equal to y2. Otherwise, it's not. If the slope is 1, then only it will be straight. So tan theta has to be 40, tan 45 1, right? In that sense. Otherwise, it might not. So now, what do you think each sample will look like? If I draw a sample, this is another sample. Now it is not straight. Another sample, and you can see the sample there also, by the way. So there is a correspondence, right? Another sample. So what has happened? I have converted the sample, 2D sample, into a line. What is this? What is this? Okay, let me give you some clue. Ignore these 3 lines at the top. Just focus on the bottom line. You see this bottom line? Focus on that. What is that? Other 3 are drawn by me. Last time I was teaching and I forgot to delete it. Okay, so just the bottom line. What do you think it is? What sample? No, see the diagram. That diagram. Gaussian, but what Gaussian? 1D, 2D. What is there anything special? This were also Gaussian. So what is difference from that to this? It's conditional. I am still representing it as 1D, sorry 2D, but it's conditional. And conditional means that's why you see this red point here. Because y1 or x1 we are conditioning on, so that is fixed. So this will not change. This is the only one that will change. Correct? So if I draw 3, 4 samples, how will that look? Now look at the other black lines. This will be fixed and this side will go up and down. And how much up and down it can go depends on the covariance. The lower the covariance, the more will be the variance. Clear? So I fixed one point because conditional. So it's like this pen, right? Simply supported, or sorry, cantilever. And then this. So this is fixed and this can go up and down. Okay? For anyone from mechanics, cantilever beam. Fixed at one end, free at other end. If you give different load or vibrate it, it will vibrate. Okay? So this is how a conditional sample will look like. So what will happen if I draw 100 of these samples and then take the mean of those? Sorry, standard deviation of those. What will be the standard deviation at the 2 points or at the left point? 0, because all the samples will be same at 1. Now remember, what was our goal? That if at some point I have samples, if I condition on that, at that point the uncertainties would be 0, there is no noise. So that thing will be satisfied if I use this conditional, because wherever I have point I will condition on that. So whatever sample I draw, this will be fixed, which means the variance will be 0. Obviously because of noise slight variance can come, but let's forget about that for now. Clear? So now you are seeing some link between the two. Obviously it's still not clear, but some link you can see. What is this, you think? What is this right hand side plot representing? Now you see many points, so what is it?
So 5D sample.
5D sample. So 5D sample can we visualize in normally we cannot. What do you see at top left? That's also a 5D sample, but I cannot show 5D, so I have taken any 2 and then plotted them. So I have just taken, I don't know what, y1 and y5 and then plotted them, because I cannot show 5D at by plotting in 2D space. Okay? But I can show 5D in this representation, and that answers the question why we need this representation. 5D, 10D, 100D, you can do that. Okay? So this is a 5D Gaussian sample shown in our new visualization. And how does it look like, this sample? Does it look like a function? No. So now you see we are going towards function if we increase the dimension. And by the way, you see a covariance matrix there? There is a special kind of covariance matrix, we will come to that later. You see some pattern there, right? It is decreasing as you go away, and diagonal is 1, and then so there is some pattern there. I will later tell you how that covariance is built. Okay, let us draw another sample. This is how it will look. Sample 1, sample 2, sample 3, sample 3, sample 2, sample 1. Clear what is happening? So, it is like a function, each sample is now becoming like a function or it looks like a function. Clear? What is this? Conditioned on x1, correct? So, I have conditioned on x1 is equal to 1 or y1 equal to 1, whatever. And now, if I draw sample, what is happening? See? So, you will see different types of variation, but that point is fixed. So, now I cannot show it with a pen, I need a flexible body, but this is kind of rigid. But you fix at one point and then you let it vibrate in a flexible kind of way. Each node can go up and down following the covariance. Clear? And it does look like 3 functions, right? I mean 3 functions, that is what it looks like, small functions, but functions. Okay. So, now let us make it 20 dimensional. 20 dimensional, I cannot show you the matrix, it will be too big. So, what I have done here is that color coded it. So, red is like 1 and then blue is like very small going towards 0 and everything is between 0 to 1 or something like that. Can be my negative also, but I do not think there is negative here, there can be. Okay. Okay. Clear? Now, this actually looks like a function with 20 points, proper sinusoid kind of thing you are saying. And see, this is a sinusoid, this is something else, another sample, this is again something else. So, the functions are having quite some variety and you are getting these functions without selecting any basis function. That is to answer your question. So, the flexibility I was talking about. Okay. Right? Condition on it. Now, what I have conditioned on? 2, y1 and y2, 2 variables. So, I cannot, so it is not essential that I will condition on 1 point, I can condition on 2 points, 3 points, 10 points, my choice, right, or your choice. And then if you draw samples, see, right, that is what, this is what we will get. And now I can draw 100 such samples, as I was saying earlier. And from those 100 samples, I can draw the mean and the variance. What do you think the mean will look like at those red points? Same, right? Because their condition on they should be same, and variance should be 0 until unless there is some noise in the data. And for other points, mean will be something mean which you get by averaging, and the variance will be again there will be some finite variance. And the variance, do you think, okay, let us take 2 variables, like let us say y5 and y20. Out of this, which one will have more variance and why? Question is clear? Y and y2 I know that we will have minimum variance, but let us take y5 and y20. So, can you tell me which one will have more variance and which one will have less variance and why? So, how many of you think y5 will have more variance? No one? How many of you think y20 will have more variance? Okay, I see many hands, others are confused. So, why do you think y20 will have more variance?
The covariance is less with y1 and y2.
How do you know that?
Because decreasing towards the last index. Like the covariance.
From this plot, look at this plot, because of blue color. Blue means is close to 0, right? So, close to 0 covariance is less between y1 and y20 or y1, y2 and y20. So, as a result, if covariance is less, they are free to move. As a result, they will have more variance, and that is what you will see.
I didn't get this one.
Okay. Let me come here. Let us look at this. Here. Okay. So, look at these 3 plots. What do you see? What do you see? Let us talk about y1. What do you see about y1? Sorry, not this. Look carefully, okay? There. This and this. What do you notice about y1?
Y1 is fixed at the point.
Point fixed at 1. What do you notice about y2? Sorry. this and this.
Y2 is changing.
Changing. Y5,
Which is also changing.
out of this which one is changing more, which one is changing less?
Okay, so in this way we are saying.
No, not in this way. First you observe it, not in this way. Which one is changing more, which one is changing less?
So Y5 is changing.
More. Why? When something changes more? That we discussed here, right? Here. Not here.
Dependence.
Here. So this plot and this plot, where the change was more? Where the spread was more?
Dependence kills it. Covariance.
So if covariance is less, then because you are fixing one. If covariance is more, because one is fixed, the other will also be kind of fixed or restrained. If covariance is less, let it be fixed. If there is almost no covariance, so it will move. Clear? So now come back to the actual question. Here, so I said you will condition on y1 and y2, okay, and you are looking at y5 and y20. Which one will have more variation? Now look at this covariance structure, the plot. Red I said is 1, and then you are going towards 0 as you are going towards blue. So between y1 and y20 and y1 and y5, which one has more covariance? y20 and y1 has more covariance.
अच्छा नहीं वो तो Y5.
y5 has more covariance, right? So that means it will have less variation once you constrain y1. Clear? And y20 will have less, which means more variation. Clear? That's all. Now when I see this plot, I have not only constrained on y1 and y2, I think also on y7 and y12. And you see that as you go away from the points, the uncertainty increases. As you stay near the point, uncertainty reduces or is less. And at the point, uncertainty is 0 because no noise. Clear? So that is the idea visually. Now you might not like this representation, you might want continuous. For example, in a regression problem, where will you get this index? You will not. What will you get? Continuous numbers. So you will need a scheme to use or have continuous number in x axis, right? This is what you are interested in. So you can have it if you define a Gaussian process now. So what I was showing was Gaussian variables, correct? If you generalize Gaussian variable to functions, so infinite dimension kind of, then you get a Gaussian process. And a Gaussian process in a Gaussian process. So in a Gaussian distribution, what are the parameters? 1D. What are the parameters of a Gaussian distribution? 1D Gaussian distribution. Mean and variance. What is the dimension of mean? 1. What is the dimension of variance? 1. In 2D, what are the parameters? Mean vector and covariance matrix. What is the dimension of mean vector? 2 cross 1. Covariance matrix 2 cross 2. ND Gaussian. What is the parameter? Mean vector and covariance matrix. Dimension of mean vector is n cross 1. Matrix is n cross n. Make it infinite, which is function. So for a Gaussian process, which is a distribution over function, what will be your mean? Infinite dimensional vector kind of, which is like mean function. So you will have a mean function. So function is like generalization of vector in this case. Okay, you can think of it like that. And instead of a matrix, you will have kernel. So generalization of matrix is kernel. That's why function is written as f of x. That's like if you have 10x, you will get a 10D vector. Sin x evaluated for 5 points, you will get 5 cross 1, a vector. Kernel is kx comma x dash. So if you have 5 points, you will get a 5 cross 5 matrix, because you will change x will take 5 point, 5 point, 5 cross 5, 25 points. So you will get a 5 cross 5 matrix. So just to summarize, function you can think of it as generalization of vector to infinite dimension. Kernel you can think of it as generalization of matrix to infinite dimension. Okay. And then if you draw x from there, take x, then it will again come back to vector and matrix. So, you will need a mean function because it is a Gaussian process now and a covariance kernel. Now, we started with mean function to mean vector to be equal to 0. So, mean function will be 0, do not need to worry about that, but we need a covariance kernel, right. Now, remember that Gaussian process is a random process that changes with time and space, or at least one of those. So, what do you expect? Things that are closer will be more correlated, or things that are away will be more correlated, or there is no pattern? Think about time. So, and weather, let us say. If it is sunny now, what do you think it will be after 1 minute? Sunny. So, highly correlated. What do you think it will be after 1 week? No clue, uncorrelated or less correlated, right. So, things that are closer should have higher correlation, things that are away will have lesser correlation. Same thing in space you can think about. Take a sample, any sample, right.
That depends on the problem.
Give me one problem where do you think it does not happen? Think and give me later. Okay. Generally in time series it does not happen. Okay. You can make a mathematical problem, but it will not be physical most probably. Or if you can make a physical problem, I will be happy to learn that because I cannot think of right now. So, think about it. If you can, let me know. Okay. I will learn something, right. So, anyways, clear. So, based on this observation, the covariance kernel is defined based on, I mean there are many ways to defining it, but one of the ways to define it based on distance. So, you can define covariance kernel based on distance. So, if 2 points are very close, they should be equal to 1 or at least close to 1, and if they are away, it should reduce. One way of doing that is what you see at the top, k. Do not ignore the I part, just look at the k part. So, that is k x1 comma x2, which has taken the form sigma square because covariance and correlation. So, if you do not write sigma square, it will become correlation. And then what you see, exponential of minus 1 by 2 L square x1 minus x2 whole square, where x1 and x2 are 2 points in time. Okay. So, or I should write x minus x prime. Okay. Now, what can you say from that structure? What happens when x1 is equal to x2? x1 minus x2 becomes equal to 0, e to the power 0 becomes equal to 1 sigma square I am ignoring, or I am taking sigma square equal to 1. What happens when x1 and x2 goes away, far away? The difference increases, negative of increases reduces, so exponential of negative reduces, so the covariance reduces, right. Now, as earlier pointed that we have to make some choice, right. In this case, this is our choice we have to make, that whether it is reducing as a square or as a mod or as let us say cube or power 4, or maybe not exponential, maybe it is changing as a polynomial. So, now your choice comes or reduces to the choice of covariance kernel. So, instead of basis function now, you have to choose covariance kernel. How and those things will probably not be covered today. I do not think I have time, but next day we will do the mathematics of this. Today it was more about giving you intuition of Gaussian process. The mathematics is coming up, there are lots of mathematics in Gaussian process, so do not worry about that. Okay. Okay, so you understand, if 2 points with this formulation I have ignored sigma square and L. So, if with 2 points the difference increases, then the covariance reduces, and if they are closer, then the covariance increases, and if they are exactly same, it is 1. Clear? And it is between 1 and 0, it exponentially decaying, it will never go to 0 obviously. Clear? Any doubt? Okay. So, now there are 2 parameters I see here, I do not know if it is visible there or not, but there is one is sigma square, I think that is visible. The other parameter you see is L. So, these are not called parameters, these are called hyperparameters. So, now you tell me why are these not called parameters and hyperparameters? No, we train them. Now you tell, we train them. That we will do later, but we train them, we do not set them. So, why are they called, what is hyper prior? Prior over prior. So, what is hyperparameter? Parameter of parameter. Okay. So, the definition you gave is for deep learning, whatever we said, but actually hyperparameter is parameter of parameters. Now, what are the parameters of a Gaussian distribution? Mean and covariance. So, what are the parameters of Gaussian process? Mean function and covariance kernel, and these two are parameters of the not 2 but 1, only the covariance kernel, because mean I have taken to be 0. So, these are parameters of the parameter. So, that is why you call it hyperparameter, and these are will be trained by maximizing the marginal likelihood, which we will discuss in the next lecture. Okay. So, what do you think will L do? There is some clue again that is drawn by me from last year, I should remove it, but what do you think L will do? What is the, how will L influence K? That is the question. What will happen if L increases, what will happen if L reduces? First let us talk about increases. So, L increases, what will happen? To understand that you have to fix x1 and x2. So, take some value of x1 and x2, fix them, and then think about increasing and reducing L and see what is happening. Covariance will increase, which means the variation will reduce. I mean, under conditional part I am saying, obviously, right. So, if the covariance is increasing, what does it mean? That points that are away are now more dependent, correct? Clear? Which means this parameter L controls that up to what length there is a significant correlation. Clear? If, or time, if x is time, then time, right. So, then what will you call it? Length scale parameter. So, this will tell that what is the correlation in the x direction, and that is why you see L I have shown in this direction. So, L tells that if I take 2 points, until what distance there exists a correlation between the 2 points. Okay. So, that is why you call it length scale parameter, because this is kind of length. Okay. Clear? Sigma square, what is it doing? It is increasing the covariance. Even if you fix L, x and all of those things, it is increasing the uncertainty, which means it is increasing in this direction, right. If sigma is more, this uncertainty will increase. That is why sigma is shown in the vertical direction. So, sigma controls the uncertainty in the vertical direction, that is the process variance, and L controls the dependency in the horizontal direction, at least in this plot, because x is in the x axis. Okay. And with this, the important thing is that you see now x need not be an integer. Previously I was talking about variable index and all those things. Now, with this kind of covariance structure, x can be a continuous number 1.1, 1.3, 1.1139, anything, and that is what you see here. See, I have written a capital X, and it is not no longer a variable index, it is more like a input variable, and y I have not shown, but y is like the output variable. So, with this setup, what you are doing is you are kind of learning the predicting y for a given x. So, you are conditioning on x and trying to predict y, right. Clear? So, I have what 15 minutes, I might start some mathematics, but let us see. So, I said that, so by the way, before I go there, let me discuss this non-parametric and parametric. So, in machine learning, we have talked about supervised learning and unsupervised learning, reinforcement learning. We have discussed that in our first and second lecture, right? That these are different types of machine learning algorithms. There are also machine learning models, there is another way of classifying machine learning models, and that is based on how many parameters the model is having. Okay. So, in linear regression that we have studied till now, that is a parametric model, because there the function is parameterized by the basis function and you decide, and once you decide, the number of parameters become fixed. So, let me repeat. In Bayesian linear regression or linear regression in general, once you finalize the number of basis function, the number of parameters is fixed, right. So, that is why that is known as parametric model. In non-parametric model, although a name might suggest no parameters, it actually means infinite number of parameters. Okay. So, non-parametric models are models that have infinite number of parameters in theory. In practice, the number of parameters is a function of the number of data point. Okay. So, let us see how in Gaussian process, let us say I have n points, n x data set of n. Okay. What will be my parameter size? A Gaussian process with n data points, xy pair, based on which we will train. How we will discuss later. What do you think will be the number of parameters? 10 points. It will give you a 10 dimensional Gaussian distribution. So, what is the number of parameters of 10 dimensional Gaussian distribution? Not 10 square, symmetry is there. So, right. So, it is function of that number 10. If I make it 11, the number of parameters will increase. If I make it 9, it will reduce. Obviously, if you include a mean, that is plus 10 or plus 9. Clear? So, that is why in Gaussian process the number of parameters changes with the number of data point you have, right. And in the ideal case you will have infinite data, so infinite parameters. Now, how do you handle infinite number of parameters? Can you handle infinite number of parameters, or even can you, I mean, if the number of parameters increases with data, and if I have a very big data set, let us say some trillion data set, I will have a function of that trillion and it might be huge. So, that might give you the impression that non-parametric models are bad, because the parameter increases with data point, right. So, at least in Gaussian process, can you tell me how do we handle it? It is already there in the previous slide and we have already discussed it. It is also there in this slide and we have already discussed it. So, how do you think we handle this growing number of parameters in Gaussian process, so that it is scalable? Anyways, Gaussian process is not scalable and we will talk about that, but so it is kind of scalable. How do you think we can do that? I gave you some clue. What do we train for in Gaussian process? So, we make the parameters function of hyperparameters and the hyperparameter is fixed, and we train for the hyperparameters. So, for example, L is one hyperparameter. Whether you have 10 points or 10,000 points, you have one L, as long as it is 1D problem. Okay. Similarly, sigma square you have 1. You have 10 points or 10,000 points, you have 1. So, you train for two things. So, instead of training for the parameters, we train the hyperparameters in non-parametric model. Clear? And as a result, the number of unknowns is never scales. And another good thing about Gaussian process is that it is kind of interpretable. For example, if I give you a linear regression model, right, what are you learning? A0, A1, A2, A3, A10, A100. But what does those weights mean? Can you assign a physical meaning to those weights? That is not a physical meaning, that is a mathematical meaning, physical meaning. Probably you can if your basis functions have some meaning. Otherwise, you probably cannot assign meaning if your basis function itself do not have a meaning. For example, if you take, let us say, if my basis function is x and I am solving a linear dynamical system, then the parameter with that x is stiffness, kx. In that case you can, But otherwise, in a generic sense, you cannot assign meaning because the basis function might not be meaningful. It just be much some Legendre polynomial or Hermite polynomial, right? So you cannot always guarantee that the parameters will have meaning. Definitely, neural network nothing has any meaning. So that's why neural network is called to be a black box. You don't even know what parameter is doing what, if there is any physical meaning to those parameters. But in Gaussian process, what you are training for? Sigma square and L, and there is another sigma, but that will come later. What is sigma square? Process variance. You know the physical meaning. It is controlling the uncertainty in this direction. What is L? Length scale parameter. It has a physical meaning. It is controlling uncertainty in this direction. So you have physical meaning here. So it is more interpretable than many of the parametric models. Some parametric models might still be interpretable depending on the basis function, but this is significantly more interpretable than most of the parametric models. Okay. So last thing is that I said that there are different types of covariance, right? And you can come up with your own covariance as well. In fact, two covariance, if you add them, multiply them, that is also valid covariance. Okay. So here I am showing you some of the covariance and how that influences. So the covariance that you see here is known as the Laplace covariance function, which is mod. Instead of square, you see the mod, and because of mod, you will see that high fluctuation, right? You can see that here, right? This is one choice. So if you have a problem for which you know that it is a time series with high fluctuation, this is probably a better covariance function. This is again another sample of that. So you can see the samples, all will have them will have, and if you look at uncertainty, it will come as piecewise polynomial because of that x minus x mod thing. So piecewise polynomial, you will not get continuous kind of thing. This is another one. This is known as rational quadratic polynomial or covariance kernel, and here you will see that at the power there is a alpha, and that alpha value you can choose, and in this case you kind of get smooth. This is what you get. Okay. Is there anything else? No. So this choice of covariance is generally driven by the data set. If you look at the data set and based on that you can decide. So again, this is in some sense more interpretable than selecting the basis function. Basis function can also be done like that, like if you know C of periodic pattern, select sinusoid or harmonic basis. That can be done, but there, even there, how many harmonic components and all those things will come. Here you know that okay, there is periodicity, select a periodic base kernel. There is also periodic kernel, and that will cater to the fact that it is periodic. Okay. There is one another property, and that is the last thing I will say, and then we will stop. So the most popular kernel, or one of the most popular kernel, is the quadratic, the exponential kernel. Okay, not quadratic, exponential kernel, the RBF kernel. And you can mathematically show that RBF kernel means that you have infinite number of bases. So you only get the RBF kernel when you have taken infinite number of bases. So that means that basis question, right? The truncation question is addressed by that. People also prefer RBF kernel because it is smooth, it gives you smooth results, it is differentiable, and all those properties are there. Okay. But now I will say Mattern kernel is more popular now, at least I feel so. That Mattern kernel has gained more popularity. There are two variants, Mattern 3/2 and Mattern 5/2. So choice of kernel is the limitation. Another limitation is data set, it is not scalable, and that we will discuss in the next lecture when we discuss the formulation. Okay. So before I wrap up, we are done actually. There will be lecture on Saturday, Wednesday routine. During practical session I will take lecture. That will account for the fact that I missed two lectures, one just before the minor and one earlier because I was not well. So for that I will take a lecture, I might take one more, but definitely this Saturday there will be lecture. Venue will be announced via email. Time is practical time 3. Okay. Any questions you have? Okay, so we will do the mathematics of this thing. Start with actual implementation and all those things in the next lecture. Okay, this was more to give you an overview. Okay, thank you.